welcome back. So this is lecture 24 in this course on Bayesian modeling, and the topic for today's lecture is Bayesian learning. So you might have heard about this term before. So the goal of this lecture is to understand what Bayesian learning means and how can we implement it in R or basically in any other programming that you want to. So we'll discuss the process of Bayesian learning and how we can implement it. Okay. So the basic idea is this, that when you define your model, you define a likelihood assumption and prior assumptions for its parameters of interest. Now this prior assumption is something that you believe or you know or you assume before even seeing the data. Okay. So what you are saying here is that, well, I do not know what kind of data I'm going to see, okay, but under the assumption that this is the underlying generative process behind the data, okay, and if this is the underlying generative process, then the likely value of theta should be somewhere in this range in order to generate the kind of data we see in such experiments. Okay, so this is our prior belief about the parameter theta. So what values the parameter theta can have? Basically, we assume a whole distribution because we treat these parameters as random variables. So it has to have some true distribution, right? So this is our prior assumption about the true distribution of theta. Okay. So we make these prior assumptions. Okay. Now, when you actually see the data, okay, then your prior beliefs will change. Your belief about the parameter theta will change because now data might tell you that the range of theta has to be in some other range. So the actual values of theta has to be somewhat else compared to what you have assumed before seeing the data. Okay. So given information in the data, you need to update your beliefs or your assumptions about the parameter theta. Okay. And how do we do it in Bayesian framework? We basically compute the posterior distribution of theta, right? So computing the posterior distribution is the same thing as updating your beliefs about the parameter theta. So you had some prior assumption about theta, okay? Now after seeing the data, you collect this information from the data using your likelihood function, and you have your prior assumptions, and these prior assumptions and your likelihood function combine to give you your posterior distribution, right? Remember, posterior is a likelihood into prior. Okay, so your posterior would be affected by the information in the data as well as your prior beliefs, right? So posterior is now your basically posterior belief after seeing the data. Okay, so you have learned from this data that your prior needs to be adjusted, and these are your new beliefs. So posterior tells you new beliefs about the parameter theta. Okay, so this is fine. So we have reached from prior to the posterior, but if we see some data again in the future, we will again update our assumptions about theta, and that will give you a new posterior. Now this current posterior becomes your prior for future data. Okay, and then you will update a new posterior, right? So that's how it works in iterations. With each data, your previous posterior becomes the prior, right? And your and the next posterior you will get will become prior for next set of data. Okay. So for example, let's say you start with the prior belief. So let me just take an example. Okay, so that will make it more clear. So let's say you are interested in modeling number of road accidents in Kanpur on a day, right? So you want to predict that how many road accidents would occur in Kanpur, let's say after 6-7 days. Okay, so on a particular day you want to predict how many road accidents would occur in Kanpur. Okay, now how do we do this? So we need to make some assumption that what is the underlying process that is generating number of road accidents in a day. Of course, it could be a very complicated process, but we can start with very simple assumption and build our model from scratch, right? From a very simple model. So let's say number of road accidents on a day I is xi, okay, and let's say it comes from a Poisson distribution. So that's our likelihood assumption. So it's reasonable to make a Poisson assumption here that it comes from a Poisson process, because Poisson process gives you number of occurrences in a fixed time period depending on underlying rate, right? So here lambda is the underlying rate of road accidents. Okay. So this is our likelihood assumption. Now we need to set up some prior assumption. We need to specify prior assumptions of lambda. So let's say our prior assumption about lambda is P of lambda. Okay. Now how does Bayesian learning works? So let's say you haven't collected any data so far, you have only your likelihood assumption and prior assumption. Okay. So what do we know about parameter lambda so far? Let's say lambda is on x-axis, prior density of lambda is on y-axis, P of lambda is on y-axis. So let's say you assume for now that your lambda could be anywhere in this range. So let's say between, let's say this 95% region is between 30 and 200 or something like that. So this is your current belief before even seeing any data. You think that the underlying rate of road accidents could be anywhere between 30 and 200. Okay, so that's your prior distribution. Now let's say you observe the actual number of road accidents on day 1. So let's say you have started recording data, and this is the data you are recording on day 1. So on day 1 you record that actually 45 road accidents occur in Kanpur. So this is data from day 1. Now given this data, you can compute the posterior distribution of lambda. How? This would be given by likelihood of lambda. So you can compute the likelihood function given the data, prior distribution of lambda divided by marginal likelihood. So this would give you posterior distribution of lambda. And let's say the estimated posterior distribution is p hat lambda given x obs. Okay. So after observing data from day 1, your belief about lambda is like this. It is your posterior distribution of lambda given x obs. And let's say the posterior distribution tells you that the lambda is likely to be somewhere around 45. So let's say the likely value of lambda is somewhere between 30 and 100, with likely value is somewhere around 45, 50 or something. Okay. So this is based on day 1 data. So this is what you have learned about the parameter lambda so far, and this reflects in your posterior distribution. Okay. Now suppose you again observe the road accidents on day 2. So you collect more data on day 2, and day 2 data tells you that, let me write it x2, okay, and let me write day 1 data x1. So I'm replacing x obs by x1. Okay. So on day 2 you observe that the number of road accidents that occur in Kanpur is actually 65. Okay. Now you will need to update your belief about lambda again, because earlier based on day 1 data it seems that likely value somewhere around 45, ranging with uncertainty that it can be anywhere between 30 and 100. Okay. Now with this new data, this has to change. How it will change? So given this new data, how your information about lambda changes? Well, your likelihood is still same. So likelihood is this, that number of road accidents on ith day comes from Poisson lambda. Okay. But what is your prior distribution? What is your prior belief about lambda for day 2? So you haven't seen day 2 data, but you have already seen day 1 data. So based on day 1 data, your prior belief will change. So prior belief for day 2 will change. So your lambda, so your prior distribution for lambda, in order to, when it comes to day 2 data, is already informed by day 1 data. So your prior distribution now becomes posterior distribution after seeing day 1 data. So, this becomes your new prior. So, the posterior that you have calculated from day 1 data becomes your new prior for day 2 data, okay, to basically infer about day 2. Okay. Now, you can calculate posterior distribution given data from day 2, which would be likelihood of lambda given data from day 2 and prior distribution for day 2, which would be basically posterior based on data from day 1. Okay. So, this becomes your new prior divided by marginal likelihood. This is what happens after seeing day 2 data. Okay. So, now the posterior of lambda will again change after seeing day 2 data. So, this will be somewhere around here. So, let us say the likely values are between, let us say 40 and 100, and most likely value somewhere around 50 or so, okay, or maybe more, 55 or something. So, this information about lambda is getting updated iteratively with each day's data, right. And now, let us say again on day 3 you observe that the number of road accidents is actually 20, then again you will do the same process. The likelihood will remain the same, but your prior for making inference about day 3 data will be posterior after observing day 2 data. That will become your new prior. Okay. And based on this new prior, you will again calculate posterior distribution based on day 3 data, okay, which would be likelihood given day 3 data, prior distribution given already day 2 data divided by marginal likelihood. Okay. So, this will keep on happening. So, as you collect data day by day, each day you are updating your information or your belief about lambda. And how you are updating it? The prior distribution of lambda before seeing day 1 data, what was day 1 data? X1, now becomes, so it is prior for inference about day 1 data. Okay. Now, for day 2 data, it becomes basically you will estimate a posterior distribution, right, given day 1 data. Okay. So, your prior belief before seeing day 1 data changes to a posterior after seeing day 1 data, right. So, this is your new information about lambda. Okay. And this acts as prior for making inference about day 2 data. Okay. So, for day 2 you observe data x2. So, your new prior after day 2 data will become lambda x2. So, basically you are updating your prior, basically your belief about lambda iteratively as you collect more and more data. So, this was your prior belief before seeing day 1 data, this was your prior belief before seeing day 2 data, this is your prior belief before seeing day 3 data, and this is your prior belief before seeing day 4 data. Okay. This is your prior belief before seeing day 5 data, and this is your prior belief before seeing day 6 data. Okay. So, this is what we call Bayesian learning. Okay. So, the prior before seeing this first set of data, okay, this prior belief changes for some future experiment. Okay. And what it becomes? It becomes the posterior after seeing this first set of data. Okay. So, the posterior after seeing x1 becomes prior for future data x2. This is what we call Bayesian learning, because your prior belief will now change, because the posterior is telling you that under your prior assumptions and likelihood and given this data. So, you are learning something from the data, and you are also learning from your prior belief what is your new updated belief about lambda. Okay. So, each of this is your new updated belief. Each of these posterior is a new updated belief after seeing that day's data. Okay. This is called Bayesian learning. Okay. So, essentially what it means, all you have to do to implement Bayesian learning is to compute posterior again and again and use posterior from the previous day as prior for the next day. Okay, that's all you need to do. Okay. So let us implement this in R. Let us implement this Bayesian learning flow in R. Okay. One interesting thing that happens with Bayesian learning is this, that if let's say your initial belief about lambda is this, right, and now each data point will point you towards true generative process, because data is coming from true generative process, right. So what can happen, well, not always, but in some cases what can happen if data is not noisy, not very noisy, is that your posterior would become narrow and narrow, basically more and more informative as you collect more and more data. So let's say this is the posterior after day 1, this is after day 2, this is after day 3, right, and let's say this is after day 4. So posterior becomes more and more informative. Ideally, our goal is to reach at a posterior distribution which is highly informative. Okay. So a posterior distribution that takes you closer to the actual true value of the parameter. Okay. But of course, if there is randomness, natural randomness in the data, you cannot reach that close in practice, right? But this is what that would happen. So for example, if you are doing some reaction time experiment, you calculated posterior using reaction time from your first experiment, and then you updated your prior beliefs, and then you collected a data, experimental data again. So let's say you do 10 experiments in a series, right? By the end of 10th experiment, you might get a very informative posterior about your parameter lambda, right? But this concept is actually related to using to the concept of sample size. Okay. Point is that either you do, let's say you start with P of lambda and you do Bayesian learning to arrive at different posterior as you learn from new data, lambda x2, right. So this is process of Bayesian learning. X1, x2, x3 are data points, are data in each experiment, right. Let's say x4, you read P of lambda x4, right. Let's say x5, you compute P hat lambda x5. So let's say this is the posterior gate after you have conducted 5 experiments, or we have observed some data on 5 days, x1, x2, x3, x4, x5. So this is the posterior gate. This posterior would be same as posterior distribution that you will get if you combine data from all these 5 experiments or data from all these 5 days and compute a single posterior conditional on data from x1, x2, x3, x4, x5, where prior on lambda is P of lambda, which was the original prior before seeing any data. Okay. So this posterior you get in the end is the same posterior if you combine all these data and you calculate a single posterior. So all these data points act as a single data set. Okay. And this is your prior on lambda. You will arrive at the same posterior. Okay. And you can do this computation, right. So basically what is changing every time when you are doing this. Okay. So let us see what is changing. So P of lambda given x1 is likelihood of lambda given x1 into prior distribution of lambda. Okay. Then P of lambda given x2 is likelihood of lambda given x2, and now this posterior acts as the prior. So P of lambda given x1. But what is P of lambda given x1? Basically, I am just writing it up to proportionality. Okay. So what is P of lambda given x1? It is likelihood of lambda given x1 into prior lambda, right. So, this is what you get after day 2. Let us see what you get after day 3. So, after day 3 it would be likelihood of lambda given x3 and prior would be this posterior. So, posterior distribution of lambda given x2. Okay, but what is this lambda given x2? This thing. So, you just substitute lambda given x3, you substitute this thing with this. So, lambda given x2, lambda given x1 into prior of lambda. If you keep on doing this, then this is what you will get after day 5. So, after day 5 the prior would be likelihood of lambda given x5 into likelihood of lambda given x4 into likelihood of lambda given x3, likelihood of lambda given x2, likelihood of lambda given x1 into prior distribution on lambda. Okay. What is this thing? Likelihood of lambda given x2, likelihood of lambda given x4, x1, x2, x3, x4, x5. Basically, you are multiplying likelihood of theta given data from each experiment. Okay. What is this thing? This is the joint likelihood. So, the likelihood for a particular value of theta given that you observe data from x1 to x5. So, you can write this thing as likelihood of theta given x1, x2, x3, x4, x5. So, this is the joint likelihood of lambda given these data from these 5 experiments x1 to x5. Okay. So, this is basically the same thing as computing posterior distribution of lambda given data from x1 to x5. Okay. So, the posterior distribution of lambda after day 5 is the same thing as the posterior distribution that you would obtain if you use data from all 5 days. Okay. So, this is a result I wanted to show you. So, what it means is that doesn't matter whether you treat each data point as something that is iteratively feeding into the Bayesian learning process, or you combine all the data points into a single database and then you compute the posterior, you would get same posterior in the end. Okay. All right. So, let us implement this Bayesian learning workflow quickly in R, okay, for the same example. So, example is about road accidents. So, let us say X number of road accidents on ith day come from Poisson distribution with underlying parameter lambda, where lambda has a prior. So, let us say prior on lambda is normal, say 150 and 50. Okay. This is prior on lambda. We believe that the underlying rate of road accidents is somewhere between, let us say 50 and 250. Okay. Now, let us say, so this is before seeing any data. So, let us say on day 1 you observe that x1 basically observed data, number of road accidents on day 1 is 45. Okay. So, let us see what would happen. So, if this is the data on day 1, now we want to compute the posterior distribution of lambda. How do we do that? Using the method that we learned so far. So, let us take a lot of values of lambda between maybe 10 and, or maybe let us say 1 and 500. Okay. So far you were using sequence function, but you can also generate just from uniform distribution, right. So, let us say you generate 1 lakh data points from a uniform distribution between 1 and rather than 500, let us say 400. Okay. So, we have vector of lambda. Now, for each lambda we want to calculate the likelihood. How do we calculate the likelihood? Using depoise, because that is our likelihood assumption for data 45. So this is our data. 45 number of road accidents have been observed, and lambda will be your vector of lambda. Okay. Now you have obtained likelihoods. Now prior corresponding to each lambda. So d norm lambda 150 and 50. So that's our prior. Okay. And unnormalized posterior then. You might have noticed that we are not computing normalized posterior anymore. We are not dividing by marginal likelihood because it does not change much. It just changes the scale of posterior densities that we calculate. But for the purpose of sampling from the posterior distribution does not change anything, because if we just get unnormalized posterior density, that is sufficient for our purpose, right? Because marginal likelihood is just a constant that we use to divide in order to get a proper probability distribution. So unnormalized posterior is likelihood into prior. Okay. So this is what we have so far. Okay. Now, do you want to compare? So let me call this unnormalized posterior 1. So let us compare the prior and the posterior. Okay. So what I will do, I'll create a data frame. Okay. So df dot post. Okay. This data frame would have, let's say, sample ID. Okay. So 1 to 1 lakh. And it would have lambda, that would be the lambda vector. It would have prior, or let us call it distribution of lambda, or let's say posterior distribution of lambda. Okay. It's a type. Okay, so type is, let's say, prior, and then distribution of lambda. So distribution of lambda is prior. Okay. So basically all prior densities. And then I will bind it. I will update this data frame. How? So new data frame which keeps everything same, but it updates it with unnormalized posterior 1. Okay, so sample IDs are same, lambda is same. Now this is posterior after day 1, which will become prior for day 2. So the distribution will be unnormalized posterior 1. So this is how I'm updating it. So I will update it after each day. I will update this thing after each day. Okay. Now just to visualize what I have done here, we can draw a ggplot. So library ggplot, ggplot df dot post aesthetic x equals to distribution y equals to, rather than calling it distribution, let us call it density, because that's more appropriate term here, right? So we're calculating prior densities, posterior densities, and all that, right? Density. Right? So x density, sorry, y will be density. On x-axis, we will always have lambda. Okay, and we want to basically draw every time a different plot for each type. Okay, so that we will do later on. So it will be geom density size equals to 1.5 plus, let's say, theme black and white plus, now we facet wrap by type. So whether it is post prior or posterior 1 or posterior 2. Right, so we facet wrap it by type. Okay, so let us run it. After day 1, let us say what happens. Okay. Oh, so I made a mistake here. So we need to repeat this for 1 lakh times. Okay. Now this should work. So let us see what happens after day 1. Okay, so this could happen if we had some type numeric integer. Okay, okay. So I'm sorry. So I made a mistake here. So this should be, rather than geom density, you can make it geom line or geom point. Okay. Now this should work. So because you have x-axis lambda and corresponding densities on y-axis. Right? See, so now you're getting these plots. So this is, the first one is prior and the second one is posterior after day 1. Okay. And this should keep on getting updated. So after day 1, it gets updated and it shows that likely value of lambda is somewhere between, I don't know, 20 and 60 or something. Okay. So this should keep on getting updated every time. So rather than 1 lakh, let us just have 10,000 just for computational ease. And here you can try geom line as well, if that works better. Yes, this is good. So this is after day 1. Now we will do the same process after day 2. Okay, and let's see what happens. So let's say on day 2 you observe x2 is, let's say, 65. Okay. X2 is 65. Let's see what happens now. Now the prior, of course, this will need to change, right? So the prior won't be this one anymore, d norm lambda 150 50, right? So the prior would be, you don't need to again get the lambda. So the prior would be posterior from after observing day 1 data, right? So those prior densities, I'm writing prior densities corresponding to those values of lambda would be unnormed posterior 1, right? And rest everything would remain the same. Okay, and this here we should write this is posterior after day 2. Okay, so this is day 2 data. Okay, and then we will have day 3 data similarly. So let's say on day 3 you observe there were 58 accidents, or let's say 70 accidents. Okay, so now okay, so this will be after day 3, likelihood will be d poise x3, and the prior would be posterior after seeing day 2 data. So the previous unnormalized posterior, right, will become your new prior density vector now, and unnormalized posterior would be likelihood into prior, which we use here, and this would be posterior after day 3. You can implement this in a R function as well, right? And the same thing after day 4. So let's say on day 4 you observe the number of road accidents is 62. So the likelihood would change like this. Prior would become unnormalized posterior from previous day, and this would again update the unnormalized posterior. And here you can write posterior after day 4. Okay, so this is the only thing that will change. This is after day 4, and then you can do the same after day 5. So let's say on day 5 you observe 70 road accidents. So this will become x5. Okay, so everything else would remain the same, and here you can write posterior after day 5. Okay, so let us run it from day 2 onwards. So let us see how it updates. Okay, so one thing you need to change here, number of rows equals to 5. Okay, so that we see them on top of each other. Oh, what happened? Oh, sorry, 6. It should be 6 because there is prior and 5 posteriors. Yes, let us zoom it. Yes, so this is what we get in the end. So this is the prior before seeing any data. This is the posterior after day 1, and this is posterior after day 2, posterior after day 3, posterior after day 4, posterior after day 5. So the order is slightly changed, so you can make it better. df post type factor df dot post type labels equals to prior, posterior after day 1, and then posterior after day 2, day 3, day 4, so on. Day 2, so that they appear in this order. Now they will appear in this order. See? So this is your prior, this is your posterior after day 1. So day 1 data says that the number of road accidents is 45. That's why it shifted on the left hand side, and then slightly shifts on the right hand side, because now consistently the road accident number you are getting are between 60, 70. And one more thing you can observe, that it is becoming more and more certain, right? So see, the last posterior is quite narrow compared to the first and second posterior, right? So this is how, so this is a model learning in the Bayesian framework. So this is what a Bayesian learning is, right? So we are learning more and more information about our parameter lambda. So we're getting more and more certain about the values, true values of the parameter lambda. Okay. All right. So this is it on Bayesian learning. In the next lecture, we will take a look at how we can specify prior assumptions on our parameters of interest, right? All right, I will stop here. Thank you.